Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, so this work is in collaboration with Sa Zhang, Kunle Elkerton, and Chris Ray at Stanford University, and I'm Chris Desa. So let's say you wanted to do inference on a factor graph. Often you'd use Gibbs sampling because it's observed to work well in many practical cases. But to use Gibbs sampling effectively, you need to know its mixing time. That is, how long you need to run it in order to produce a good result. Unfortunately, it's difficult to decide what the mixing time of a model will be. Because of a lack of theory, no one really knows if Gibbs sampling will be feasible for a particular model. What we came up with is a new way to measure a factor graph that gives us a theoretical understanding of Gibbs sampling. This measure, the hierarchy width, characterizes only the structure of the underlying factor graph, and bounding the hierarchy width is sufficient to ensure that Gibbs sampling will mix in polynomial time. This furthers the understanding of the problem by giving us a new class of models where Gibbs sampling is guaranteed to work. So the hierarchy width condition roughly breaks down factor graphs into three classes. To gain intuition, let's look at an example of each one. Factor graphs with constant hierarchy width provably mix in at most quadratic time. Factor graphs with hierarchy width proportional to the logarithm of the number of variables provably mix in polynomial time. Finally, some factor graphs with unbounded hierarchy width, linearly proportional to the number of variables, are known to take an exponential amount of time to mix. To see how hierarchy width interacts with real problems, we constructed three models for the same knowledge-based population task, one in each of these three categories. In this plot, the green series for the model with hierarchy width proportional to the problem size has a much larger estimation error than either the red series, which represents the model with log proportional hierarchy width, or the blue series, which represents the model with constant hierarchy width. And not only do the low hierarchy width models mix rapidly, but they also can produce high quality results. A model with log proportional hierarchy width has recently been applied to real problems, yielding competition winning results. To follow on these results, we also give you a way to generate models that provably mix in polynomial time. We introduce hierarchical templates, a new class of factor graph template that always produces models that have bounded hierarchy width. This lets us easily construct models that provably mix in polynomial time. So to recap, we proposed a new factor graph parameter, hierarchy width, with which Gibbs sampling can be shown to mix rapidly. So if you want to learn more about how to construct Gibbs samplers that work, come to poster 47 tonight. Thank you.
I'll be talking about joint work with Tamara Broderick and Michael Jordan. The title of our paper is Linear Response Methods for Accurate Covariance Estimates from Mean Field Variational Bayes. Mean field variational Bayes provides approximate inference by casting inference as an optimization problem where we minimize the Kullback-Leibler distance between the true posterior and approximating factorized posterior. This method has proved attractive because of its fast runtime on large data sets. However, it's well known that even when it provides good approximate posterior means, it dramatically underestimates posterior variances, and by construction, since the posterior factorizes, provides no covariance estimates. As a simple example of this, consider estimating the locations of a mixture of a two-dimensional Gaussian. A sample data set is shown on the left there, and imagine that we want to get the posterior of the locations shown in red dots. We simulated a number of data sets. On the rightmost graph, each simulated data set represents one dot, and on that data set we fit an MCMC model, a Gibbs sampler, which we consider to be the ground truth, and a mean field model that assumes that the posterior factorizes. The graph shows the standard deviation, and as you can see, the mean field model dramatically underestimates the standard deviation of this location component. Linear response methods provide a simple closed-form correction to the mean field covariance matrix. The formula is shown on the left. In the formula, you have two terms. You have sigma VB, that's the original mean field underestimated covariance matrix, and H is the Hessian of the expected unnormalized log likelihood. Each of these terms are generally easy to calculate and sparse. The sparsity allows you to, in many cases, solve this linear system in time that's linear in the number of data points, even when the number of latent variables in your model scales with the number of data. And as you can see on the graph on the right, the green dots represent the linear response standard deviation estimates for that component on the same model, and they match the MCMC results at a small fraction of the time. We've demonstrated that linear response methods work on a wide variety of models, providing accurate MCMC-like covariance estimates, but in variation-based time. The linear response methods generalize classical methods from statistical physics to exponential family approximating distributions. The original posterior need not be exponential. In fact, the key assumption, and the only assumption that you need, is that the mean field approximation produces good estimates of the posterior means. We encourage you to come to our poster to talk more about the theoretical background, to see many more example models, and to talk with us about your modeling problems. We're interested in using this on more problems in the future. Thank you.
I'm Mingjun Zhong. I'm working with Nigel Goddard and Charles Sutton. We propose a new method called latent-based melding to combine two different models where the variables of the models are connected by a deterministic function. One model is called individual model. So, for example, we use a hidden mark model to model a sequence data S here. So, and the other model is called population model. So that the idea is that we use national survey data to model some summary statistics tau of the sequence S. One example is the time of the S, which the states stay in the one of the states of the two states in the HMM. So this could be just the normal distribution. And at the same time, tau can be is a function of the S. Here is the just sum of the sequence S. So then we have the distribution tau and the PS, and also the function F here. So our question is to how to combine P tau and PS. So we could employ the posterior regularization. And also, we could use another method. It's called base melding. So the idea is that, on the one hand, we have the distribution P tau. On the other hand, we have distribution PS and the function F. So this will induce a new distribution for tau, which is P tau star. Then we combine these two different distributions for tau into one and pull back to the individual model in the space S. So, but the base melding assumes there's no latent variable, and instead, it's quite often there's a latent variable in Casey. So, like the mixture model, and we still can use the base melding, but there's an intractable integration here. Instead, we propose the latent base melding and derive a joint distribution over S and Casey, and we show that there's no intractable integration, and S and C can be inferred simultaneously. If you're interested to come to my poster, number 25, thank you.
All right, so I'm Phil Bachman. This is joint work with my advisor, Doina Prekup. I'm from McGill. And the paper is called Data Generation as Sequential Decision Making. So primarily this paper is kind of a work in two parts, I guess you could say. The first section of the paper is a collection of mathematical analogies, providing kind of a framework that might help people view a variety of techniques that have been introduced for training deep generative models in kind of a more unified and cleaner way. And then likening those to techniques that have been developed recently also for performing reinforcement learning. So this is based around the fact that deep directed generative models are powerful. They represent structurally complicated distributions by composing simpler ones. And we interpret directed models as policies for constructing data. So these policies essentially act by sequentially setting or configuring a model's latent variables in a sequence of decisions where you kind of condition the outcome of each decision on previous decisions that were made. And training these kind of sequential decision-making policies is just the domain of reinforcement learning. So on the slide here, I have a couple of pictures of different distributions where you're sort of sequentially refining a very vague distribution into something finer grained and more precise. So the second part of the paper is just kind of showing these ideas in action and developing a couple of models for performing a task called imputation, in which you're trying to predict the value of some unobserved data, and then kind of applying these techniques for training these directed generative models via this kind of guided policy search. So what we do is we develop stochastic recurrent neural networks that construct predictions sequentially via iterative refinement. So the models kind of make a prediction for what the missing data is. They compare it to what they're looking at. Then they refine that prediction about what the missing data is. And they do this repeatedly. So it's kind of a stochastic feedback loop that we're training to produce the correct outcome. By constructing predictions sequentially like this, the models can naturally capture higher order structure without having to add post hoc MRFs or CRFs. So rather than training the model on its own and then sticking an MRF or a CRF or something on the end and kind of fine-tuning that, we just train the model jointly end-to-end to produce this kind of structure in the output distribution. So we train these models using a form of guided policy search, or equivalently, at least in this particular context, you could also interpret this as stochastic gradient variational Bayes. So I guess if you want to hear more, you can come and talk to me at the poster. The sort of mathematical analogies in the paper are a little bit dense and require familiarity with the surrounding work that they involve. So I recommend that.
Hello, everyone. My name is Sixing Zhang from Cron Institute, NYU. My collaborators are Anna Koromonska and Jan LeCun. I'm presenting a new method called elastic averaging SGD, which distributes the training of large neural nets on GPU cluster. The basic idea is illustrated by this diagram. We have P workers running in parallel and a central parameter server. The workers run SGD with Nesterov momentum asynchronously. Their loss function has an L2 penalty. It is an elastic term that attracts the parameter of local worker and the central parameter toward each other. All local workers see the full data set in different order. In order to reduce the communication overhead, each worker communicates with the central server every tau mini-batch update. The central parameter is updated with the moving average formula whenever it receives a parameter from a worker. We now illustrate the basic elastic averaging property on quadratic loss in 2 dimensions with Gaussian noise. On the left, we plot the trajectory of the global average parameter x in red and the local parameters in blue. We see that the global average parameter has a smaller variance near the optimum 0. On the right, we combine Nesterov momentum method with elastic averaging SGD. We observe that the central path in red is even less oscillatory than the local parameters. Moreover, the whole system is more stable due to the elastic averaging property. Finally, we apply both asynchronous EA-SGD and EA-MSGD to train large convolutional neural network on ImageNet dataset. Our baseline is MSGD, the Nesterov momentum SGD on single GPU. We also compare with the downpour method of Dim and others on 4 GPUs. We see that the elastic averaging SGD in red has similar performance as downpour in green, but our methods require 10 times less communication. Remarkably, After combining with Nesterov momentum SGD, our method in orange achieves not only the fastest convergence rate, but also the smallest test error. We first posted our paper on arXiv about a year ago. We have learned that a number of companies, including Facebook and others, have implemented EASGD and are currently using it in production to train large neural nets. However, its theoretical aspect is still not fully understood. Please come to our poster number 37 this evening. Thank you for your attention.
So hi everyone, my name is Yin Zhen, and this is a joint work with Miguel at Harvard and also my great supervisor Rich. So Zubi has given a great lecture this morning about Bayesian inference, and the core problem in Bayesian inference essentially is to compute the true posterior. However, for most models that we are interested in, including neural networks, the true posterior is intractable. So now here we consider approximations, and in particular, I show the approximation structure on the right-hand side that we will replace the typical likelihood terms with simple factors. So an idealized way to update these things, we think, is to first take the true posterior, and then you remove one of the likelihood terms, replace it with a simple factor, and then you update that simple factors to make the new distribution approximate the true posterior. So this will give us very accurate approximations because right now, the factors can capture the effects of its corresponding likelihood terms on the true posterior. However, it is also an intractable procedure as well because you also have the difficult terms in the red box. So in practice, we run EP, which takes the same idea, but replace the difficult likelihood terms with simple factors. So now EP has much cheaper updates than the idealized procedure, and we often have analytical solutions. But more importantly, EP can produce most accurate approximations on a variety of problems, so it is a very important technique in approximate Bayesian inference. However, it is a shame that we couldn't apply this thing to large-scale inference problems because it has order and memory. So we solved this memory overhead problem by proposing stochastic EP, where we tie all the local factors and then run CP on it. So now we just need to store one copy of the local factors. That means we no longer have the number n in the memory complexity number, so then problem solved. So the core idea here is that now the factors are approximating the average effect of the likelihood terms on the true posterior. And during training time, each iteration, we will sample one likelihood terms to do stochastic updates. And importantly, we need to mention that the relationship between stochastic EP and EP is the same between stochastic variational inference and variational inference. We test this algorithm on a variety of examples, and to summarize that, stochastic EP performs pretty much the same as the original EP, and both of them are better than ADF, a simplified algorithm. We also tested the memory reduction numbers, and in the largest example, we saved 65 gigabytes memory comparing to the original algorithm. So to summarize this, we finally managed to scale this very accurate EP algorithm to the large dataset settings. So we are very excited about this. Come to the poster and workshop to talk with me. Thank you.
All right, so I'd like to tell you how we automated variational inference using Stan. This is joint work with my amazing colleagues, Rajesh, Andrew, and Dave. So if we want to use variational inference in practice today, we're kind of faced with the picture that we see here. We want to fit a statistical model to a large data set. Well, we hand both of these things to a PhD student. She toils away at the mathematics and the coding and the debugging, and many months later produces a result. If we make any changes to the statistical model, this poor student has to repeat this process, and this really is inhibiting the use of all of these nice variational techniques today. We propose an automatic tool to, in some sense, replace the poor PhD student, or at least give her some free time. It's called ADVI, Automatic Differentiation Variational Inference, and what we do is we take the things in this list, which consume the time of the PhD student and automate them using the techniques that you see beside them. I'd like to emphasize that ADVI, we've implemented it as part of STAN, which is a probabilistic programming system, and I'll tell you a little bit more about that in the next slide. What ADVI does is it paints a new picture for us. We can now take any statistical model that we write in a probabilistic programming system, in this case STAN, and instantly get a variational inference algorithm. No derivations, no coding. This allows us to close the loop. Our goal is to genuinely, rapidly, iteratively explore new models as we investigate large data sets, and ADVI is bringing us one step closer towards that goal. So what does STAN code look like? Let me walk you through a very simple example. This is a toy model, a graphical model on the left, where we have n observations xn. These are discrete observations, so I went ahead and placed a Poisson likelihood on them. The latent parameter that we'd like to estimate is theta. It's a positive real rate value, so we've declared it as such in the parameters block. And because we can, we make no conjugacy requirements in ADVI. I've placed a Weibull prior, which I doubt anyone else in the room has done. So given this, we give it into ADVI and automatically get a variational inference algorithm. Nothing else is needed. As expected, ADVI is faster than MCMC techniques, especially for data sets with large number of observations. And I again like to highlight that ADVI is currently part of STAN. I encourage you to visit the link below and let me know how it goes this week at NIPS. Thank you.
Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.